Okay, so welcome to 479, Stat 479, Lecture 6. And so today we kind of finish off the first major topic, which involves linear models and linear regression. And so this will kind of cover everything you need to know for the first homework, which focuses on these linear models. So in particular, we'll kind of summarize what we've talked about for the last 3 or 4 lectures. And then we'll talk about how, we're going to introduce this tool of simulation, which is going to be very useful to validate different methods. And this is, again, something that you're going to be doing in the homework as well. So that'll kind of round off our discussion on linear models. Then I'm going to briefly just overview the course structure, just kind of what you can expect over the next 18, 20 lectures or so. Just, part of that's included in the weekly schedule, but I just kind of wanted to go over that briefly. And then we're going to move on to our next kind of big modular topic, which is generalized linear model. And so we're just going to kind of introduce that and I guess stop when we've run out of time. So just to recap, we've been spending the last probably 2-3 lectures talking about linear regression or linear models. Once again, we're in this, we refer back to this framework that kind of has 4 components: the data, the statistical model, the estimator or algorithms, and then the analysis. So let's kind of review that. So for the linear regression, we're in this supervised multivariate setting. So we have p variables and 1 response, and there's n samples for these. So our data we can kind of conveniently write in matrix notation as x is an n by p matrix, which is the covariates for each sample, and y is the n-dimensional vector. So the linear model the statistical model that we focus on, we're in kind of this linear regression or linear model setting, is just this standard linear model, which is just y equals xb plus epsilon. So the response depends linearly on the features. That's kind of what that means. And so b is a p-dimensional vector. That's the parameter of interest. These are just the coefficient weights. And epsilon here is the noise variable, and that's going to just be an n-dimensional vector, 1 for each sample, and it's going to be 0 mean. And then we also talked about possible assumptions. So obviously mean 0 is something we assume throughout. And then we looked at various different kinds of examples. So we looked at assumptions like independence and homoscedasticity, which is that if you look at the covariance matrix of epsilon, we use this notation sigma, but we assume that it's sigma squared times an identity matrix. This involves like independence and all of the noise variances being the same. The other one, assumption that we considered was when you have kind of multivariate normality, where epsilon is just a multivariate normal with some mean 0, obviously, and some covariance matrix sigma. And then the estimators or algorithms that we saw 2. So we focused a lot on least squares, which is just, you're minimizing the squared L2 distance between y and xb. And then we also looked at maximum likelihood, which is essentially like maximum likelihood requires you to know the distribution of your data. And so here we assume that epsilon's multivariate normal. That's in general the most natural assumption for when you have a linear model. And in that case, the maximum likelihood objective ends up still being quadratic, but it's weighted by the covariance matrix. So in this scenario where you have, sigma, like this covariance matrix sigma is the identity times a constant. This is just the same as the least squares objective. But if you have more general covariances, and you will have that up to some degree in the homework, then you're going to have this extra factor of sigma to the negative half. Then, we talked about, like, particularly in the previous lecture, we focused on specific algorithms to find this. And so what's nice about this scenario, and it won't be that nice in the other scenarios that we'll see throughout the course, is that solving this problem just involves essentially inverting a linear system. So there's lots of different methods you can do. from your point of view, you might think, well, all you really need to do is to just, type in, like to just invert a matrix on your computer. And that's certainly one way to do it. But we wanted to look a little bit more at how that inversion can happen. And so we looked at one such algorithm, which was gradient descent. And one of the reasons for looking at that is that we're going to see this algorithm throughout the course a lot. And we found that, the gradient descent update was kind of, again, because we have a quadratic, we get nice linear updates. Okay. And so this is all for least squares, and in your homework you're going to derive these for both least squares and maximum likelihood in a specific scenario. And the previous lecture really focused on specific properties of that gradient descent update. So we showed a good choice of step sizes to ensure that we get convergence. So we found that needs to be valid. Okay. And finally, a couple of lectures ago, we spoke about, we looked at the analysis. And so what analysis means is, questions like how close is beta hat to B or B hat to B for various scenarios. So we found that if you have that, if you had that you're in the independent homoscedastic noise case, then we were able to show that that the least squares estimate has this nice property that you can just, there's zero bias, and then the variance is given by this expression, and here we're assuming that X transpose X is invertible. And then we also found that, we, in terms of other metrics like the mean squared prediction error, what was nice about this is that this didn't depend on the on properties of the matrix X at all. It just depended on sigma squared, P, and N. And similarly for the out of sample prediction error, we were able to show that we again got an expression for the out of sample prediction error that only depended on sigma squared P and N. And then if we were in this second scenario where was multivariate normal, then typically we'd use the maximum likelihood. So what we were able to show, and in particular, if we looked at this again simplified case where the sigma was sigma squared I times n by n, then whether you remember that maximum likelihood and least squares were the same, so I'm not going to have any subscript for this. So we had that, so I'll use beta hat LS here, but it could also be true for maximum likelihood because they're the same. The nice thing there was that you could actually derive the distribution, which allows you to do inference. Okay, and And this was sometimes referred to as like this pi x, or the hat projection matrix. Okay. And so this kind of is a summary of the main results that that we derived throughout the last couple of lectures. So that's just kind of a good summary and a recap of what we did, and also puts it into, it kind of rounds things off by putting what we covered into this this statistical framework that that we've liked to use throughout. Okay, so the next thing that we're going to talk about is something that's very useful as a tool, and it's going to be very useful in this course. So we derived expressions for, like, the mean squared error and mean squared prediction error, which we could kind of do in this case because things were nice and linear and reasonably simple. But in practice, you often can't calculate these in closed form in any reasonable way. And so a natural question to ask is, if you wanted to say I ask you the question, like, compare the maximum likelihood versus the least squares estimate in a particular scenario. And that's something you are going to actually do on this homework. Like, if you can't actually do the calculation, it's which you won't always be able to do, then how do you actually evaluate it? So remember, for example, that the MSE is just this expectation, and this expectation is taken over the noise of okay, so that's the definition of MSE. But how do you take expectation using, like, how do you actually take expectation using a computer instead? Because computational tools are often, when you can't actually find closed forms, computational tools give you the answer, and we're going to kind of, or give you an approximation to the answer. And so the way that probability simulations work is it tries to estimate this expectation. And this is a very, very widely used tool in statistics in general, not just for this this scenario. So so the idea is pretty simple. So rather than computing expectation exactly, so generate many, and I'll use this notation, n realizations. So this big N is different from the little n, I want to say. So generate many realizations, and then take an average. And this idea is pretty simple intuitively, but it's certainly something that is very powerful and is used throughout statistics, and you will see this in action on this homework. And this general principle will be used a lot throughout the course on your homeworks. So the general idea is that So like, let's consider this example, which you are going to see in the homework of the linear model. So there you have, you typically have this this equation. So you have, okay, this is your linear model. And so you want to generate big N realizations of this model. And then how do you get those different realizations? And the idea is that since epsilon is random, you get n different epsilons. Which gives n different data sets. So I'm going to use this notation. It's a little bit annoying that I'm going to use this subscript notation right now, but it's like, because we've typically used subscripts to denote the covariate index, but now we have a third index, which is the simulation realization index. So I'm going to just say, so you generate n different noise variables, okay? And then you say if beta b is fixed, and x is fixed, which it will be in the homework, then you're going to get n different y values, y1, y2, up to yn. And note that these are not different. These are like, this is not like little n, which is the sample size. This is big N, which is the number of realizations. Okay, so you have now, so n data sets. X, Y, we'll use this subscript k, k equals 1 to n, where, x is obviously in r to the n by p, little n by p, and yk is in r to the little n, okay? And so these are n different data sets, and then therefore we can generate n different b hats. So we're going to get, b hat 1, b hat 2, b hat n. And again, this notation is a little bit awkward because it's not referring to the covariate index here. It's referring to the simulation or the realization index. And then we can say that to find if we want to find this expectation for then we can just say that this is approximately 1 over n summation. We're going to use k equals 1 to n. Okay, and so you can do this for any algorithm or procedure. Okay, this is a very useful tool, and then the idea applies to any model or a performance metric. So whether you're talking about mean squared prediction error, out of sample prediction error, or anything else, your you can use this simulation tool as a really good way to kind of get a good estimate of this mean squared error. And again, this is something that you're going to use throughout this course. Okay, so again, you're going to do this for your homework. So by the time you've done your homework, you'll be pretty comfortable with this tool. I just wanted to give you an introduction to it, so that you don't go in and think, what on earth are we doing and why are we doing it? Okay, so that's it for so that kind of covers everything from the first big topic, which is linear models and linear regression. A lot of the ideas that we developed there are going to be used throughout the course. So kind of getting on top of these initial ideas is really important. So we've covered everything that you need, hopefully, to do homework 1 at this point. And now we're kind of moving on to the we'll shortly move on to the next topic. So I just briefly wanted to talk about the course structure. And so I guess why I bring this up is that for statistics or data science courses, there is a kind of theory methodology side. And there is okay, so the reason why I'm bringing this up is that it stems from this general kind of question or thought that for any statistics or data science courses, there's always kind of a theory methodology side, like which methods do you use, how do you evaluate those methods, why do you use those methods? But then there's also like a scientific application, real data set side. Like, you want to apply these methods to real data sets and kind of see how they work with real data. And so, when you take a course like this, multivariate high dimensional statistics, you'd ideally like to kind of span both. So ideally we focus on both. And this is often quite hard to do because kind of the theory methodology side typically is very sort of black and white and mathematical. Whereas the scientific application real data set side is really more nuanced, and you have decisions to make that are not black and white, and you kind of want to find a good way to make those sort of data driven decisions. And so in that case, because of that, it's often quite hard to teach them together. And so what I'm going to do for this course is that the first 16 to 20 lectures, and this involves the 4 to 5 homeworks, we'll focus on theory or methodology. And then the last, and so 4 to 6 lectures focus on dealing with real data sets, and that's really the course project will involve this. So in some sense, like, the way the evaluation method works is also kind of consistent with the way these lectures are going to work. That the first 2/3 to 3/4 of the lectures are going to focus on theory and methodology, and you're going to be evaluated on this through the homeworks, and that's worth 50% of your grade. And then the last sort of roughly quarter of the course the lectures are really going to focus on issues of how to deal with real data, because that's more of a kind of a gray, nuanced thing than sort of the black and white aspects of theory and methodology. And this will be evaluated really through the course project, because in the course project you're going to have to you are going to actually use the methods that we talk about during the first 3/4 of the course. We're actually going to use those in practice. So that doesn't mean that the theory isn't relevant to the project part of it, because the theory and the methodology provide a lot of guidance on how you're actually going to determine which methods to use in your project and how to implement them and that kind of thing. But we're going to really sort of focus, our starting point will be, here's this scientific problem in a real data set, which methodology do we use to apply that? And so whereas in the first part, we've really focused on this framework, which is entirely theoretical and mathematical, and we talk about a data generating statistical model and really use that as a basis for designing kind of everything. Whereas really for the last 4 to 6 lectures, we're really going to start with a data set and a scientific problem, and then really try to use that as a basis for determining which method to use. So I hope that's kind of clear. So in terms of what you can expect in the course, really then, the first 3/4 is going to be very heavily focused on, the kinds of things we've talked about in the first 5-6 lectures, which is, very much mathematical, theoretical. And then the last, quarter to a third of the course will really be more about how do we kind of apply these methods into practical applications. And we're going to see 1 or 2 examples of that. So I hope that's clear, and let me know if you have any questions about the overall structure and kind of what the expectations are. So the next topic is okay, so this we're kind of adding a little bit more complexity to what we had before, where we're still in this supervised multivariate setting, but now we're going to look at potentially different kinds of a slightly more general class of models, which are generalized linear models. So not just the linear models that we saw before, these are generalized linear models. And what's cool about this is going to tie very much to convex optimization. I touched on that at the end of the previous lecture, because it's really a sort of a nice segue into this part of the course, where convexity is going to be a big important property, and that's going to be useful in when we talk about kind of algorithms, such as gradient descent or other algorithms. So once again, the data that we're dealing with here is multivariate supervised data. So now we're using the original notation where the subscript denotes the covariate index, whereas the superscript denotes the sample index. Okay, and so once again we can write this as as in this convenient vector matrix notation. Okay, but then the question that we're interested in here is that the linear model or least squares works well when data is or data y is continuous, spans the whole real line, and is close to normally distributed. I mean, we saw that least squares actually corresponds exactly to maximum likelihood when you have multivariate normal data. But in practice, we often don't have this. So yi may be binary. So for example, voting. There's lots of examples of binary data, like whether a medical diagnosis is successful or not. Whether you vote yes or no to a particular bill. There's lots of scenarios where you have binary responses. Then you could also have count data. It's like counting weather events, crime events. Sorry, just kidding. Okay. Or non-negative. So like the normal distribution, like the range of the normal distribution is negative infinity to infinity. But often in practice, you might have non-negative data. For example, like lifetimes. Lifetime's clearly going to be a positive quantity. Like you might have like size of fire or other event. And typically these sizes are going to be non-negative. So are there ways to kind of deal with this non-negative data? And so hopefully, if you think about this question a little bit, from what you've hopefully covered in 309 or any other probability course, Math 431, or any probability course that you've seen before, other distributions so other than normal, are useful to account for other data types. Okay, so for example, Bernoulli, that's perfect for binary data. Poisson or binomial, they're very good for count data. There's many others, and if you have non-negative data, you might consider the exponential or the gamma distribution for non-negative data. Okay, and so in a nutshell, So to fit different data types, basically the generalized linear model framework incorporates these distributions into the modeling framework. So so we're going to say let P be univariate distribution. So we're going to be univariate at times when we discuss this, because distributions like the Bernoulli, Poisson, binomial, and exponential or gamma, you've kind of only really learned in the univariate case, and actually generalizing them to the multivariate case is quite challenging. But so we let P be univariate distribution. And then we're going to let yi is basically going to be this distribution and then we're going to look at each of these features. So we're going to say x of I, j, and then multiply them by bj. Okay, and so what this is going to be, we'll call this the parameter of the distribution. Okay, and we're gonna talk a little bit more specifically about what that is. Okay, and once again, we're going to assume that I equals 1, 2, up to n are we're going to assume that they are conditionally independent. Given the given x x1, x2 up to xn. Okay, so that's going to kind of allow us to write this to write this out to write out this distribution more clearly. Okay, and so we've actually seen this. So we're going to tie this back to the example of the linear model. If we consider the linear model, and then we essentially looked at maximum likelihood and least squares for the linear model, we essentially have the model that yi is normally distributed with mean sigma squared, and so this corresponds exactly to multivariate normal xb sigma squared I n by n. Okay, so this is kind of exactly the scenario that we looked at, and so here we'd have that p is just normal with mean mu and variance sigma squared. Okay, and so sigma squared is fixed and known. Okay, and so now for generalized linear models, GLMs, P can be more general. So, for example, Poisson or Bernoulli or anything else. So I'm just I'm just going to kind of remind you of what those distributions are, and you may have kind of learned them before. So I'm just going to focus on Poisson and Bernoulli for now, but we'll make this a lot more general shortly. So recall, for example, Poisson lambda. So we need to assume that lambda is bigger than 0. This is kind of like a rate parameter. So what we have here is that, sorry, let me use this notation. This means that our distribution function p of y, and I'll use this notation lambda to say that it depends on this parameter lambda, is e to the negative lambda to the y over y factorial. And then this is for y equals 0, 1, 2. So this holds for count data. And then if y is Bernoulli p, for example, so here p refers to probability of, so p here is between 0 and 1 because it refers to the probability of success. Then I'm going to use this notation. It's a little annoying because we have a little p here, and then I've used the notation p to be the the distribution as well. So that equals to one way to write this, it's equal to 1 if so it's equal to 1 with probability. So let me just write it up properly. So the probability is just going to be p for y equals 1, and it's going to be 1 minus p for y equals 0. And there's a kind of a clever or convenient way to kind of write this out, because you know that y is only 0 or 1, so y is binary here, so y is in 0 or 1. You can write this as p to the y times 1 minus p to the 1 minus y. You can check if you plug in y equals 0, you get exactly p and 1 minus p for y equals 1 and y equals 0 respectively. So one of the challenges here is that can you just set lambda equals to make this consistent, use our covariate information? It's tempting to kind of say, let's just let lambda equal to some j equals 1p xji times bj, or p equal to some j equals 1 to p, and then xji bj. But how do we guarantee that p is between 0 and 1 and lambda greater than 0? Because I mean, the x's are just covariates, they can be anything, and the b's are also just they're the feature coefficients, they can also be anything. So this leads to we're going to spend kind of the rest of this lecture and most of the next lecture talking about a really interesting and cool class of distributions, which the Poisson, Bernoulli, and normal are all examples, but there are lots of other examples too. And these are called the exponential family distributions. And that's going to help us actually deal with this issue. Okay, and so some of you may have seen this before. A lot of you may not have, and that's okay. But this is a really nice way to summarize, to tie to generalized linear models, and they also kind of link to convex optimization, as I mentioned, because they have this set of distributions has a lot of really nice properties. So I should say a univariate distribution. So we're going to be univariate for a while. So I know this class is multivariate, but the distribution P, remember, is univariate. And so a univariate distribution P has parameter P theta, so we're going to use this notation P theta of it's an exponential family distribution. If it has the following form. Okay, so this is one of those things where I'm going to write this out, and it's going to look potentially pretty mysterious if you haven't seen this before. So we're going to kind of write out the definition first, and over the next lecture or so, we're hopefully going to gain a lot more intuition about where these expressions kind of come from and why this set of distributions is really powerful and really useful, and we're going to see a lot of examples throughout. So let's first write out this definition. So I'm using this notation P subscript theta of y. So theta is the parameter that kind of denotes the distribution. We're going to see that it's going to be related to quantities like P and lambda. So what makes it an exponential is that the distribution has an exponential in it. And so okay. So this is what the distribution looks like, and there are these different components which we're going to talk about. So h of y, that's referred to as the base distribution or base measure. Okay, we're going to see some examples of this shortly. This is referred to as the parameter. And more specifically, we'll actually see it's the natural parameter. I'll explain where that notation, like where that kind of language comes from. There's this, which is what's referred to as the sufficient statistic. Why it's called sufficient statistic is not super important. We will touch on it briefly, but we'll see that calculations will be pretty easy, and we'll see examples of this. And this is actually probably the thing that's going to be most important that we're going to see throughout. And this is referred to as the log partition function. Okay, and again, at this point, this is just a definition to you if you haven't seen it before. And you might think, like, what in the hell is this? But really, it's just kind of, it's a definition that we're going to unpack and see lots of examples of shortly. So let's see some examples of this in action. So we're going to start with y is distributed Poisson lambda, which we've just seen. So we know that P lambda of y, and I'm going to use lambda and not theta, and you're going to see why shortly. And so the question is, can we write this out as an exponential? So the way we typically do that is if you take an exponential, if you want to get things into an exponential, you can always just take a log of whatever that expression is and then exponentiate it. And so that's exactly what we're going to do. So, if we take an exponential, then take a log, you can see that this can be written as, there's no, you can just pull out the y factorial, and then you're going to have y log lambda, and then minus lambda. Okay, so one thing to note here is, so this is our base distribution or base measure. Y here is our sufficient statistic. So okay, now this is actually our theta. So theta here is log lambda. And so what that means is that lambda equals e to the theta, because we want to invert that expression. And so we can actually, because it doesn't really matter how you parameterize the distribution. So if you let lambda equals e to the theta, and this notion of reparameterizing distributions is, again, hopefully going to become clearer over the next few lectures. You can write this out as 1 over you can write this out as p theta of y equals 1 over y factorial x above y theta minus e to the theta, okay? And so this is going to be your a of theta. So for Poisson, we can see that, we have that h of y equals 1 over y factorial, and remember that y equals 0, 1, 2, and so on. And this is actually a probability distribution in itself that corresponds exactly to the case where you have theta equals to 0. And then you have your sufficient statistic t of y equals y. And then you have your log partition function a of theta equals e to the theta. Okay, and so we've expressed this Poisson distribution as an exponential family. Now we're going to do the same thing with the Bernoulli. So now let's look at the Bernoulli. Bernoulli P, and then remember that I said that we have P of y here equals P to the y times 1 minus P to the 1 minus y, because, we know that we're only dealing with y is 0 or 1. And so let's again, if we want to exponentiate this, we can take logs and then take exponentials, and that exponentiates everything. So we can rewrite this as equals x of log of p to the y times 1 minus p to the 1 minus y. And so that's going to be, when you're dealing with logs, that multiplication and powers become really easy to deal with. It's just going to be y log p plus 1 minus y log of 1 minus p. And so we want one expression that has a y in it, and then one expression that doesn't have a y, like anything to do with y in it. So because we want, if we look at this expression, this first expression has a y, has something to do with, or if we go back up, we have t of y that depends on y, and then we have theta. So the way to think about it is you want to split it up into a part that has a y but no theta, that's your h of y. Then you have a part that has both theta and a function of y, and that's your kind of theta times t of y. And then you want to have something that only has a theta in it, and that's like your a of theta. So let's do that here. So we can re-express this as y times, you can see that there's a log p and a log of 1 minus p here. And once again, subtraction is pretty easy to deal with for logs. That just corresponds to division. So that's just log of p 1 minus p. And then you're going to get plus log of 1 minus p. Okay, so you can see that h of y here just equals 1. There's actually no term that has no that has something to do with y and p. So your base measure here is just 1. Okay. And now your theta is given by this expression, log of p over 1 minus p. Okay, and so this has actually got a very nice interpretation. This is referred to as the log odds ratio. That's just kind of some nice intuition, and this actually has a kind of a nice interpretation to it as well. But we're going to kind of unpack this a little bit more as we go. And then we ideally want to write, a of theta is going to be negative log of 1 minus p. And then we're going to, we need to express this in terms of theta. We're going to express this in terms of theta, okay? And so how are we going to do that? So we know that theta equals log of p over 1 minus p. And so that means that we can say that, we want to kind of invert this expression. So let's invert it. And so the way that we can do that is that we can rewrite this as e to the theta. So that means that so whenever you're trying to get an expression, the best thing to do is to is to kind of try to get p all on its own, and so that means that and so then what we get is that p is equal to so p is equal to e to the theta over 1 plus e to the theta. Okay, and so notice that this is clearly going to be between 0 and 1, which is what we expect. Okay, but what also like and so if we put that into a of theta equals log of p over is just negative log of 1 minus p, which is also just the same as log of 1 over 1 minus p. That just is going to be equal to log of 1 plus e to the theta. Okay, so for Bernoulli, we have that h of y is equal to 1. Once again, we have the sufficient statistic is just equal to y, and a of theta is equal to log of 1 plus e to the theta. Okay, and so we end up with, so we can rewrite this, the Bernoulli distribution is p theta of y equals exponential of y times theta minus log of 1 plus e to the theta, using this transformation that theta equals log of this log odds ratio, log of p over 1 minus p. Okay, and so this is this is pretty cool. This kind of gives us a different way to write this distribution out. And the last thing I'll say, which is kind of cool and kind of interesting, is to note that if we know that that p is in 0, 1, notice that theta, which is log of p over 1 minus p, that can actually be anything in that can actually be any value from negative infinity to infinity. So remember that we had that issue earlier that we couldn't really set p is equal to summation of x times beta, but now we have a theta which is in negative infinity to infinity. So we can set theta equals to summation j equals 1 to p in reparameterized distribution. Okay, and the absolute last thing I'll say here, and we'll go into this in a lot more detail in the next lecture, is that, recall Poisson. We'll go back to the Poisson example and see if the same thing happens there. So we have that, if we look at it in terms of lambda, we get e to the negative but then if you look at it in terms of theta, sorry. Okay, looks like something's going on here. Sorry, yep, okay, so fix that. So then, if you look at things in terms of theta, sorry about that delay. And then you have this relationship that lambda equals e to the theta, or theta equals log of lambda. Note that if lambda is greater than 0, but theta, which is log lambda, which is in negative infinity to infinity. So therefore we can say that, therefore once again we can set the theta is just this, if we set theta like this, then this is reasonable since no restriction on range of theta. Okay, and this is the key idea behind GLMs. Okay, so that'll be everything that I talk about today, and we'll delve into these issues in a lot more detail regarding exponential families and generalized linear models in the next lecture. Okay, thanks very much.